Hello, in this lecture we will discuss open Newton-Cotes formula, and as an example of open Newton-Cotes formula, we will discuss rectangular method or midpoint rule. So rectangular method or midpoint rule is an open Newton-Cotes formula. Open Newton-Cotes quadrature does not place an xi at endpoints of integration at the limit points, for example, the limit point A or B. For the integral, as we have discussed in the previous lecture. So open rules for quadrature allow the possibility of setting n is equal to 1, that is for one rectangle, or you can say for one trapezium, giving the simplistic midpoint rule. So in the rectangular rule, we approximate integral using a single interpolation point A, the left hand point of the interval. So if we take an interval of integration from A to B, so we can say that this xi cannot, we avoid to replace xi on these interval points A or B. And number two, there is a possibility of setting n is equal to 1 in open Newton-Cotes formulae. So let's discuss the rectangular method or the midpoint rule. So rectangular approach is a simple technique which divides the area into vertical segments or strips with the height equal to the function value at the midpoint of each strip. The area of the rectangles can then be calculated and summed to estimate the total area. So it's simple to understand. The area under the curve or the function will be divided into rectangles, and then we will estimate the area of these rectangles finally to get the integration of this region. So in this approach, it is assumed that the value at the midpoint provides a valid approximation of the average height of the function for each strip or rectangles. So this strip can be shown as a rectangle. So as with the grid method, mean the graph methods with the small boxes, refined estimates are possible by using more and thinner strips to approximate the integral. So we can suppose that y is equal to f of x be a given function, and its graph is drawn in the figure 7.1 as shown. So here this curve is actually the function y is equal to f of x, and area under this function or graph is represented with two rectangles. So one rectangle is ABDE. You can shift this point E here, so you can say ABDE. The other rectangle is BCEF. So just note that the area which is not exactly calculated, like this one, this will be considered as a approximated error. Okay, because this area is not included in the rectangle. So it means if we will increase the number of rectangles, the accuracy will be higher. And if we take number of rectangle in less quantity, so the error will be increased. So if we can say that h, the width of the rectangle, or the step size. If the step size is less or lesser, we will have a degree of accuracy up to a good limit. But if we take this width not smaller, then we can increase the error or we can lose the degree of accuracy. So area under the curve initially can be calculated as area of rectangles ABD and BCEF. We can start in deriving the formula for two rectangles. So that's why we have divided the area under the curve into two rectangles. Also, we can mark the point A as x0 and point C as x2, and x1 is the part lies between x0 and x2. So the interval AB is divided into two subintervals. Now, if we mark point A, B, and C with x0, x1, and x2, then we can write integration from A to B f of x dx is equal to x0 to x2 f of x dx. And then the area of this first triangle is f of x naught into h plus area of the second triangle is f of x naught into h. So because this is the common side for two rectangles, so we can use it only once. So area of the rectangle, this one just height into width, and area of the rectangle, the second one, height into width. So then we can write h into f of x naught plus f of x1. If area under the curve is divided into four rectangles, that is for n is equal to 4. So it just has to write this formula, okay, two times. So for four rectangles, we can write x0 to x2 plus x2 to x4. So f of x dx plus x2 to x4 f of x dx. And simply we can write hf of x0 plus f of x1. So this is for two rectangles. And for the next two rectangles, we can include f of x2 plus f of x3. So in general, for n is equal to k, rectangular rule will take the form as given below, that is f of x0 plus f of x1 plus so on f of xk minus 1. So next, as an example, we can calculate the area of integral 0.5 to 1 x4 dx. And how we can calculate? We need to calculate the step size. So if the number of rectangles are 4, so then the step size will be 0.125. And we can tabulate the values. For example, so if we take these four rectangles, we will have 5 points. Okay. We will have four points. So for n is equal to 4. So x0, x1, x2, and x3. So the first point is 0.5, and the next point will be 0.5 plus 0.125, which will be 0.65. And the next point is 0.65 plus 0.125 will be 0.75. And the next point 0.75 plus 0.125 is 0.875, and the next point will be 0.875 plus 0.125, which will be exactly equal to 1. So now we can calculate the value of the function. For example, if x is equal to 0.1, so f of 0.1 will be 0.1 power 4, because the function is f of x is equal to x4. So f of x naught plus f of x1 plus f of x2 plus f of x3, so can be calculated as 0.1397075. Note that exact value of the integral is 0.521 x4, which is the analytical value. So an error can be calculated as the exact value minus approximated value, which is 0.054043. Similarly, we can evaluate this integral. So for n is equal to 4, so the step size is 0.125, and then we have a different point 0, 0.125, 0.25, because if we start from 0, the next point is 0 plus 0 minus 0.5. Okay, so then we we will add here. So this should not be, okay, this is the value of f of x at point x naught, and this point x1 is obtained by adding 0.125 in 0. So then adding 0.125 in x1, we will have x2, then x3. So now substituting the values in the formula, so we get answer equal to minus 0.262643. Here is the error is very low. So similarly, we can have another example. Evaluate the following integral using rectangular method. So 0.75 to 1.3 sine square x minus 2x sine x plus 1. For n is equal to 2, the step size is 0.275. So starting from 0.75, the next point is 0.75 plus 0.275, which is 1.025, and then 1.3. So calculating the value of the function and substituting in the formula, we have a rapid solution 0.5295269378. So next is the example of closed Newton-Cotes formulae. So what's the difference is that uh, we will present some methods that can be used to approximate integrals. So closed Newton-Cotes quadrature strategies require the value of n should be greater than or equal to 2 to avoid dividing by 0. So here we can also make a difference between open and closed Newton-Cotes formulae, that in closed Newton-Cotes formulae, the number of trapezium must be equal to 2 or greater than 2. So the first closed Newton-Cotes formula is trapezoidal rule. Trapezoidal rule So trapezoidal rule is the first and the simplest version of the Newton-Cotes closed integration formulas. So trapezoidal rule can be easily derived by geometric representation of function in the sense that area under the curve will be divided into trapezoids or trapeziums. One way to improve the accuracy of the trapezoidal rule is to divide the integration interval into a number of segments and apply the method to each segment. The trapezoidal rule is applied extensively in engineering practice due to its simplicity. It can easily be translated into computer code so that integrals can be evaluated rapidly. Let y is equal to f of x be an integrable function on the interval a to b such that x lies between a and b. To evaluate the desired integral, a to b f of x, the interval x lies between a to b will be divided into n equal subintervals of width h is equal to b minus a over n. So this is the step size. So again you see we have a curve y is equal to f of x, and area under the curve, if we initially divide into two trapezium, we have the first trapezium AB ED and the second trapezium BC EF. And again we can mark with 3 points x0, x1, x2. Okay, and the interval is a to b. Trapezoidal rule. So to approximating the area of the trapezoid under the curve connecting f of a and f of b, area under the curve can be calculated as area of trapezoids ABD and BCEF. So area of trapezium ABDE plus area of trapezium BCEF. So this can be written as integration from a to b with integration from x0 to x2. Okay, because this interval AB is now subdivided into two intervals, x0 to x1 and x1 to x2. So we can have the area of the trapezium, that is sum of the two parallel sides multiplied by width of the trapezium divided by 2. So the parallel sides, f of x0 this side and f of x1 is this side. So that is why we have here, so f of x0 plus f of x1. And because this side, the common side is sharing between the two trapezium, so that is why we again start with f of x1. So for the second trapezium, so this is area of the first trapezium, okay, and similar area of second trapezium is h by 2 f of x1 plus f of x2. Taking h by 2 as a common, it is easy to summarize the formula, and if we increase the number of trapezium to 4, so we can write the formula for n is equal to 2 twice. That is from x0 to x2 plus x2 to x4. So from x0 to x2, so this is the formula we can write as it is, and from x to x4, so we can start from x2 to x3 plus f of x4. So then we can take a common h by 2. So we can simplify f of x0 plus 2f of x1 plus this 2f of x2 plus 2f of x3 plus f of x4. So here we note that with the first term the multiplier is only 1, and also with the last term the multiplier is 1, and the remaining terms in the intermediate terms are multiplying with 2. So it is easy to generalize that we can just remember that the first and last term will not be multiplied other than 1, and the other intermediate terms will be multiplied with 2. So that is why we can also write as h f of x naught over 2 plus so on. So it depends on the user how he likes to write it. Okay, if we apply this trapezoidal rule to solve this problem, so for n is equal to 4, so we need to calculate the step size, which is b minus a over n pi by 4 minus 0 over 4 is equal to pi over 16. And we can tabulate the data. So 0, 0 is the first initial point, and the next point is 0 plus pi by 16. Then 0 plus pi by 16. So it should be pi by 16. So then we add this pi by 16 into pi by 16. So we will have this pi by 8. So then we add this pi by 16 into pi by 8. So we have this value, and then we will have finally pi by 4. And corresponding value of the function we can write as f of x naught, f of x1, f of x2. Okay, so this should be pi by 16. Okay, so then after calculating these values, we need to substitute in the formula and we will have the answer. And if we calculate this uh, analytical answer of the function, so we will have this value 0.151746, and the difference between the two values will be considered as the absolute error, which is 0.00405. And similarly, for this question, the step size is pi by 16, and again here should be pi by 16, not pi by 6. And the corresponding values is calculated, and if we substitute these values, we have 2.06510. And the analytical value of the given function can be calculated as the traditional manner, and this value is 1.6316, and the difference between two values is 0.4332. And similarly, the next problem is calculated by trapezoidal rule. Again we take this 4 trapezium, and the step size is 0.25. So the initial point is E, and the next point is E plus 0.25, and the corresponding value of the function is calculated as. So here we have the approximated value is 2.8603, and the analytical value is 2.58. Analytical value is 0.27. So this here is a difference. So maybe there could be some mistakes here, but it is easy to understand how we have to calculate this values of the function. So this is the trapezoidal rule. In this lecture, we have discussed rectangular rule and trapezoidal rule, and we have solved different problems to understand how this rectangular rule or midpoint rule works. So I hope it is not difficult to understand.